we've got this. Okay, we're starting the lecture, obviously, and hopefully I'm not going to overload my computer like I did last week. I'm running a lot less stuff. The only thing I'm not paying attention to this morning is when that came on, and I'm just trying to ignore it for now, not restarting my computer. But one of the things I wanted to do was at least come back to this. I didn't really get a very good chance to talk about this. I also changed my mouse settings back to the ones I used to use, so I shouldn't have that jitteriness. It was an experiment, and I didn't like what it did. But remember last week we were talking about how periodic sequences involve this, fundamentally they involve this definition right here, that a sequence, you can pick it up and slide it backwards and forwards any multiple of n. You don't have any homework problems with this question this time around, but I think in set number 2, which I posted last night just to have things in the queue, and perhaps on the first exam, so I didn't want to leave you hanging too badly on thinking about this. And then the sinusoidal periodicity characteristic, I'm just seeing, is it periodic? So what I do up above, and we went through this last week, I just simply replaced n by little n plus capital N. And that equality sign there is really saying, is this true? You know, I'm going to find out what conditions will make that true, right, from trigonometry. It's really like there's a question mark. If you were doing this the way you might do it if I was working on the board. And this I can't control because I'm using the browser here. So I can put a question mark. Well, wrong spot. I'm not going to try right now. Too frustrating with that. But is this equality? There we go. I can do it that way. Is that true? So that's what I did last time. That's in the blue box there. That just says it has to be a rational relationship. And we talked about that as a practical matter. It would be saying that if you were sampling the sinusoids, that your sampling clock is rationally related to the frequency of the sinusoid you want to generate. And there's 2 of you taking the lab, and in the lab, the very first real-time experiment, which is lab number 3, you will generate a periodic sinusoid because you're going to use a lookup table. You're going to have a table that has samples of the sinusoid in it, like n samples. I think maybe it's 64, and then it just keeps playing those same samples over and over again as the interrupt service routine fires in the real-time part of the loop. It just keeps pulling another value out, pushing that out to the digital to analog converter, and when it gets to the end, the table wraps around with a modulo and it starts all over again. So but if that's not the case, then you don't always have that situation. But it's just a nuance, and the other thing that came with that is this idea of indistinguishable frequencies. This is not the same as the periodic property, but it's just saying that because in the discrete time domain, in the way we're generating the cosine, we always have this property that we can shift the little omega naught by any multiple of 2 pi, so that leads to these indistinguishable frequencies down here, or distinguishable frequencies, I mean. So if you have a period of n samples, it just says that you can generate different frequencies, omega sub k, starting at 0 and going up to n minus 1. And I guess a good way of thinking about that would be, again, if I was thinking of this lookup table, I could stride across the data. If you have an array of data, and each time you come through the loop to take that data out and send it to the D-to-A converter, you could take one, then the next one, and so on. If you decided to just stride by 2, you would take the first one, then the third one, then the 5th one. So you'd be taking every other sample. Then you could increase that by 3. And then finally, you could go all the way up to the limit where you're striding the whole length, and so you're just taking the same value each time, and that would be like DC. You'd be taking the same value, putting out a constant, or in between, you'd be putting out all these other intermediate frequencies that are related based on the fundamental period, or the length, in this case, of the sequence. What I was going to say about that is, later on, when we study the fast Fourier transform, we'll see that these are the frequencies associated with the fast Fourier transform, which technically the name for it is the discrete time Fourier transform, or DFT. I said that wrong. Discrete Fourier transform. Discrete time Fourier transform is later in this chapter too. That's continuous in frequency, whereas the discrete Fourier transform is discrete in frequency. So that plays into that a little bit later. But just to sort of reiterate what we did last time, oops, didn't want that turned on. So I took an example, and I wrote this out last night when I was reviewing stuff, and I put this in over here. So I just said, okay, what about those two frequencies for omega sub k, because that's what is right over here. That's this plot right here. Those plot identically, and yet it seems kind of weird that it would be that way. Well, it has to do with the indistinguishable frequency idea. It's definitely a periodic sequence, and we can establish that from this formula right here. We can just, well, not that one, this one up here. We can establish that that's true. We have 2 pi k over n equaling omega naught. So in this particular case, we can identify what we've got in this problem. And what did I just say? Get this back on again. That was what I was doing down here in this case. Pi over 4. Why is it not doing that? So let's just go back up here for a second and just see what I mean by that. In order to get it to match this equation right here, what I have to do is I have to be able to pull out a 2 pi on the top. So how do I do that? If I pull out a 2 pi, that means I have to do what? If I want to plug this omega naught in there, I have to make it look like 2 pi times something. So how can I do that? I can just multiply the top and the bottom by 2, right? And then I'm going to have 8. So in this particular case, that would tell me what? That the period here would be 8, and 1 is the value of k that makes this thing work. I think I did that right, but yet I thought it was 16. Maybe I'm thinking of another problem.
Well, they had omega naught as 5 pi over 8, so.
Yeah, I'm doing this one right here, the 7 pi over 4. So 2 times that, 1 over 8, and then if I do the 7, I'm going to mess around with that one right here. So you find what I'm doing right now, I'm just proving that it is periodic, and I can establish what that fundamental period is, that it's 8 in this case. So yeah, I'm thinking it's 16, so where am I missing the 2? It is 16. So what did I do wrong over here? Pi over 4 times n, put the 2 pi on the top, multiply by 2 on top and bottom, I get 2 pi over 4. I'm puzzled as to why I'm not getting 16 down there. Does anybody see what I'm doing wrong? I mean, I'm going to run the example here, which is what I was heading towards. Let me just run the example. This was a notebook I had open last time, but I just did some hacking in it this morning. And I took this basic cell and I actually added a cell above it. This is kind of a common practice for me to put a little cell on top just so I can do like a calculator and type a few things in just to see what's going on. But I went ahead and put in I decided to put in pi over 4, and this is 2 pi over 8. So, and then I'm going to put in pi 7 over 4, and I'm going to run the index of n from minus 20 to 20, and I get identical for both, and I do get 8. My head is bulging a little bit. It is exactly 8. I don't know what I was thinking of a moment ago, but how do I get 8? There's the beginning all the way, and there's the very last point right here. So that's 8. 1, 2, 3, 4, 5, 6, 7, 8. So period is 8, and this is what I get for pi times 1/4 and pi times 7/4. So how can those yield the same thing? Well, I'm going to jump back over to here and just show you that if I put in the 7 pi over 4, because of the periodicity, the cosine function, I just come along and I say, let me transform that by subtracting 2 pi from that argument. That's fair, right? Because it's a mod 2 pi function. And then I just simply put that over a common denominator, 7 pi minus 8 pi over 4, and I'm left with minus pi over 4. But cosine of minus pi over 4 is cosine of pi over 4 because it's an even function. Now, does this work for an arbitrary phase angle, or does it work for sine? If I plug sine in there, what's going to happen? Sine of minus pi. Exactly. Does that make sense? Let's just prove that, though. I mean, I'm just going to do this for a moment because I'm going to say to you guys, check things out, because it's very rewarding to do a little simple math model and just prove it to yourself. And that's what I like about Jupyter a lot, is that I can go do that pretty easily. So let's just do that. Let's just go in here, replace the sine, and I'm just running it, and it's inverted, right? No surprises. What's another thing I did in here? I vowed when I did this morning. I took a cell and I started hacking it, but what's a good thing in coding to do? If you got some code that works, comment it out and add a replacement here and there.
Yep.
Why would you do that? Because your brain will forget what you had to begin with, and then how do you get back to it? So what's a neat thing about this environment? In most coding editors, there's a keystroke that does that. And in the case of Windows, it's Control and the slash key, which is down in your lower right. So I'm just hitting it repeatedly. And see, it's just block commenting. And Jupyter does another kind of nice thing. If this cell is the way it was the last time I ran it, the color bar there is blue, saying, you're good, you ran it, don't run it again. But notice if I change this, now it's at least highlighting me and letting me know, hey, you didn't run this because you made a change to it. That can be helpful, because one of the things about Jupyter that is very sloppy is that variables become globals in here, and they're available up and down the entire notebook. And you change them somewhere up here, but you don't rerun a calculation, and then down below you're using it in a calculation, and you've now got things out of sync. So I think the developers added this color thing to kind of jog your memory to make sure you update everything. if I had forced you to use the Pluto notebook in Julia, it has a different paradigm. It's all the variables have to be unique, and it will complain that you define another variable and it's not the same as the one up above in purpose, and then everything tracks perfectly through. But it's a different paradigm, and if you go on the internet, you'll find people have complained about both sides. I mean, people do things to make it convenient. So I'm now going to jump back to where we were and speed along through where we were in these notes quite a bit. Turn this off so I don't start writing. We talked about these definitions, and I'm going to come back to them when we talk about some of the homework problems. I will say, though, that problems 2 and 3 on the homework involve causal and bounded input, bounded output. These are the definitions, strictly speaking, but we're going to be momentarily jumping into the case of linear time invariant systems. When you have a linear time invariant system, you've got a special case. The system obeys the time invariance property and is linear. So when those two properties are true, then you get help in terms of seeing if the system is causal and seeing if it's bounded input, bounded output stable. And I guess mathematically, those are like theorems. You have a theorem that goes along with something being true, and then you can use it to speed your way. And that's problems 2 and 3 are that. But I have to go through some stuff here before we get into that. So LTI system, it has the properties like I just said. It's both linear and time or shift invariant. So turn this back on again. I like time invariant as language better than shift invariant. I originally thought LSI was a cool way of saying it, but that's confusing because if you're taking IC design, long time ago it was named, large scale integration. But to you guys, you probably don't maybe even know that term. Is that still used? The LSI, it's in there, but when I was growing up, TTL logic was the beginning of integration, and it ended up being called SSI, small scale integration. Then there was medium scale integration, and then large scale, and then very large scale. I mean, that's an alphabet soup for engineers in particular. Our acronyms get reused a lot. I won't go into that because there's some things in common usage, and I don't want to offend anybody, but it's true. I mean, these acronyms get used enough that you get very confused by them. And I know the engineering terms for them. So when we have linear time invariance, the common thing to do is to now have associated with it, with the LTI system, the impulse response. And the impulse response to me is like a signature. So you have this box sitting here. If it's an LTI system box, it could be an analog circuit, it could be a digital discrete time system box. So for us now it's a discrete time system box. We have an input, we have an output, we have this box in the middle. So what we can do is characterize it with the signature by pinging it with a single delta going in and then looking at the output. And that is for, oops, keep getting this confused. Maybe I'll start using the other editor again. I don't know, this is causing me a little bit of a grief. So you set the input equal to that. You assume the system is at rest, and then what that returns is the impulse response. And to me, this is a kind of a crude example, but if I tap my finger like that on this board, I'm essentially shooting an impulse into it by that sudden spike from my finger. And then if I was recording the vibrations on this piece of wood with a microphone, that would be the impulse response of this board being my LTI system. Is that kind of okay? It's mechanical, it's acoustics, but it's still the same idea. Or another good idea is when your car goes over the railroad tracks or through the potholes, which we have plenty of those around town, you could think of that simplistically as a single, pulse like that. And what does your car's suspension system do? It reacts and you bounce up and down a little bit. That would be the impulse response of your suspension system, approximately so. I mean, a delta in the continuous time domain is an approximation to the mathematical notion of the delta function. And in the case of discrete time systems, it's very precise. So we're pinging it with this delta. So now we bring into the definition, or get what the response is mathematically. And this is problem 1 in the assignment. We expand x of n, like we talked about last week, or 2 weeks ago, whatever, as a delta sequence, time shifted, and then weighted by the individual inputs, x of k now, k being an independent variable, or a dependent variable that we're summing over, and n is the independent time variable. So plug that in and wrap our system operator that we were talking about last week. Probably cheated you a little bit on that. This is the book's notation for a system. It's a box that has an operator T, and T is just the letter they chose. I don't really even know why they chose it. It could be anything, but it's just an operator, and an operator is a function. So it says, how do we map the input to the output? And that's what T is doing. Is everybody good with that? Is there a better letter than that? In calculus, it was F, right, all the time? You were integrating F, differentiating F of X or something like that. So down below here, we've just chosen T. And so now what we can do is, the trick is we're going to put T on this side, on the left side, and that will, by definition, produce y of n. And then on the right-hand side, we'll put T right up in here, wrap it around the whole expansion. And this is the beautiful thing about this expansion, is now we can make some headway and simplification based on the linear time invariance property. So T wraps around the whole thing, and linearity tells us that we can superimpose various responses into to form a composite response. So the T operator says, this x of k is just a gain scale, in effect, because k is a dependent variable on the sum index. So the T operator is sitting right out here, and it looks at this and it says, I'll go right inside of there. Remember the karaoke machine idea I talked about last week? Maybe you don't like my idea, but I came up with this over 10 years ago. Karaoke machine, if it's linear, second singer can come up and sing with you in the karaoke machine, no distortion, and it's the same as just superimposing one singer and then a second singer. And that's what we're doing here. We have x of k is the gain of an individual, a time index k. And so the T operator goes around that because it's a linear time invariant system. And so we're making use of linearity when we can pull this out in front and let T move to the inside of the sum. Then we come along and say, what about time invariance? Well, if the system is time invariant and we're applying a delta sequence at the input, shifted to k on the n axes, no problem, the system will respond identically whether we apply it at k is equal to 0, 1, 2, 3, 4, or backwards in time. It's a time invariant system. So that just says that this thing together produces the h of k due to time invariance. And that is the end of the story, except get this thing to erase for me. No, it's a stray mark. Now we have the same thing. If we interchange the variables, we would have two definitions of the same response. We can say that in general, if we have the impulse response, which is the signature response of a system, we can form a general response for any input through this formula called the convolution sum. And the upper version is what we just developed, and then if you go in and change variables in the sum, remap things, change the indices and so on, then you can flip it around. So you've got two different versions to do the same thing. This is not a new idea. X convolved with H is the same as H convolved with X, is what we would say. In DSP, though, the convolution means an operation which is this summation, which is, either one of these two forms, whichever one is suitable. And we're going to go through an example right now, but do you want to do that one or do you want to do that one? It's going to depend on what suits your fancy in terms of how you see the problem breaking apart and how much you would enjoy doing it one way versus the other. It's good if you could do it both ways in practicing, but I want to stop and pause just for a second here and talk about convolution sum. Does a real-time DSP system have to do this specific convolution sum? This is a question, just to see how you're thinking about it right now.
We could have a lookup table where it depends. We're assuming we're doing real-time processing.
Yeah, you could do that. We'll have what's called a difference equation here coming up shortly, too. So the difference equation is the discrete time version of the differential equation, and what does the differential equation respond to from continuous time circuits and systems? What? No, that would be the Fourier transform of the impulse response, which we'll be getting to eventually, but I'm more simple than that. You have a circuit that you put together with inductors, capacitors, resistors. You claim this is an input point and this is an output point. If you were going to mathematically analyze the input to the output, you would, through linear constant coefficient differential equation theory, you would develop a differential equation model, right, to go from input to output. In the discrete time domain, we end up with a difference equation model. Same exact idea, though, linear constant coefficient difference equation. And those are just a couple of pages away from here, but, and that's an algorithm, okay? So think algorithms in DSP at all times, because that's how we make things buildable. I mean, that's how we actually implement them. We have an algorithm to do something. The mathematical concept might be the difference equation, and what we are doing abstractly in a math sense when we apply an input to a system and we have its impulse response, we're doing this convolution sum. So the convolution sum is more or less an analysis tool to get the output from the input and the known impulse response. In practice, though, we have the system represented in a box as a difference equation which cranks an algorithm. We can put any input in we want, we can get the output. We don't really have to have the impulse response, although that ends up being involved in an indirect fashion. So this blue box equation, the reason why I'm spending time on it is it does factor into doing some modeling and simulation, but when you're implementing something, you're not going to implement this convolution sum. What would jump off the page at you right now just looking at that form? What is potentially a super annoying thing about this? I see the infinity signs and I say, wait a minute, how can I do that? I mean, every time I want to calculate an output, I can't just sit there and run an infinity number of cycles. So this is an analysis tool, is what it boils down to. Understanding this is fundamental, But in the end, it's not the means by which you're going to implement something, but it's an understanding, though. And it's an understanding that's worth getting a little bit tuned into. So the example that I took here in the notes is convolving a pulse with an exponential. And the role that I took on this example, as I said, the pulse is going to be the impulse response. So it's a u of n minus u of n minus n. So that is a pulse of n samples. And the input is an exponential decaying pulse. Exponential decaying as long as A's magnitude is less than 1. But in the end, whether I'd make X the rectangular pulse and H the exponential, that'd be, I should have done it that way, is what I'm getting at. That would have made more sense physically. Then I could talk about sending a rectangular pulse into an exponentially decaying impulse response, and that would be kind of like firing a pulse through an RC low-pass filter in the continuous time domain, because you know the RC low-pass filter has an exponential for its impulse response, right? I mean, it's kind of burned in your brain from some point in time when you first look at the RC low-pass filter and establish its impulse response, or get at it as the inverse Laplace transform of its system function, or the inverse Fourier transform of its frequency response. That's probably one of the things that makes this chapter hard to get started with, because we're not doing anything in the frequency domain, we're not doing anything in the Z domain, which would be like the Laplace domain. Those come just a little bit later, so we're thinking very simplistically, because just got to get started with a bunch of stuff. And the bunch of stuff is a bunch. I don't know how to say it any other way. It's a lot of things you're trying to, massage around and get going. So if I could confidently draw here, I would try to draw this, but it's probably not going to work out all that well. Okay, so that's h of n, and then I guess it's just a skill I have to learn how to do on this thing. Okay, and this is the a to the n u of n, and we're going to convolve those two together. Some specific things to talk about here is that one is a finite duration signal, that's the h of n, and the x of n signal is semi-infinite, so it starts at 0 and it goes out to infinity. So that makes for some interesting issues in doing the convolution sum. So the first thing in doing the convolution sum is you back up and say, what form do I want to take in the blue box up here? Do I want to do x convolved with h, or do I want to do h convolved with x? So in my case, I decided to take the first form, so that means I have to time reverse this pulse and leave this one alone. And I'll be doing this guy right here then. Right? So I need to have that info into the expansion. So I went off and drew the pictures probably on a sheet of paper somewhere or another and said, okay, now I know how to do this. I forgot my water bottle on my bike today, and there's no drinking fountain out there anymore, so I'm maybe going to be struggling to swallow here shortly. There's only this used bottle of water over here. Not even Dr. Trimboli can give me anything, and our front office had nothing in it. And the vending machine for $3, I can buy something I don't want to buy. I don't want to buy anything but water. I can't get it. But we'll see how it goes. So first off, might be a question, is everybody okay with taking a function, time reversing and shifting it, and then putting it on a sheet of paper? I'll just give you a really quick hint on that, though, over here. Since this is my normal PDF drawing tool, I know I could run this a little bit better. So we start off with a vision of h of n versus n, but now if we're doing the convolution sum, we're going to be summing over k. So now we need to draw the picture of h of n minus k. So this guy right here, in mathematics or signal processing, sometimes people call this interval from 0 up to n minus 1 the support interval, or it's the active interval for the rectangular pulse. So a good way of being able to draw the picture is to think in those terms. If I take h of n and then I replace its argument by n minus k, all I have to do to figure out what's going on now is I just have to say I can go to that, right? Just replace n by n minus k, and now I want to focus on what's going on as I change k. Some of you have done this before, and if you haven't done this for a long time, I'm just trying to get your brain wrapped around some things you can do to get started. Because when you're doing a convolution sum type exercise where you're doing analysis on a problem, you have to be able to draw a good picture, I contend, in order to set your problem up. Thank you.
You're welcome.
Is that from the coffee machine or what?
No, that's from the dispenser right there.
Where is that? No, I'm going to pour water on my computer.
Don't do that.
You can tell me later.
Forgiveness.
So the idea now is I want to be able to draw an accurate picture. Rectangular pulse, you can kind of guess at it, but what I would do now is I would just go down to here and I say, okay, k, I'll just work from one side of the equation, n minus k is equal to n minus 1, or k is equal to, I'll flip k to the other side so its sign goes away, and I'll bring n minus 1 over, so n minus the quantity n minus 1, right? You good with that? And then I'll get the other one going here by saying n minus k is equal to 0. That's from this side. And then I'll be able to say k is equal to n. Good? Have something that you just can hold on to and never let go of it. I mean, you know, you can always go do something like this. Am I seeming too ridiculously simplified? I just want you to have something that will get you started and you won't get stuck. Because if you get off to a bad start, everything is bad from then on. And if I'm grading exam problem or anything, I immediately have to figure out, okay, step 1, hosed it up, bad from thence on, so how do I give partial credit? I'd like to see the error occur further towards the end. And you'd like to make your error closer to the end so that when you have to backtrack, you get it resolved much more quickly. If the error was made way at the beginning, you're just beyond frustrated. And working in Python, in the error messages you get in the screen in the Jupyter are very much like that. They always go to the most recent error and you can trace it back and then you can figure it out. But you got to also get tuned into how that tries to help you too. Because in the beginning, I think every coding person knows that if there's something that they don't like about the way error messages come back to you. So at any rate, I have it in here, then I have the unshifted one, and now I'm definitely good to go. So the idea is this is moving across the screen. So as n increases, that pulse is going to move across, and it's going to engage the fixed part of the pulse, and you have to answer a number of questions on this. And I'm looking at my chord, deciding how I want to do this. So fundamentally, what's going on here is you have to consider n in different values for n. So n less than 0, no overlap. N greater than 0, I get partial overlap as long as n is not large enough to bring that value into the inside of the x of k signal. And then, so there's really just 3 cases in this problem. There's 3 cases that you have to consider. Some cases only have 2. The homework problem number 1 only has 2 cases to it. And I'm going to lead you right up to it in an example, and I'm going to force you to do the last step, which is evaluating the geometric series. But we're going to get started on geometric series review right this moment. So guess I should pick a good color. I'll pick orange. So this is part of our solution right here. For n less than 0, no overlap, so no output. Next case, n greater than or equal to 0. We're actually going to have n between 0 and n minus 1. So we're going to make sure our pulse is straddling, which is the picture I'm showing down below here. The pulse is partially in this k greater than or equal to 0 and partially hanging out the back end. And then the third case is going to be where this pulse is fully inside the exponential. Do those jump off the page to you? And I know you might be thinking, and I'm thinking too, because what am I doing in my job right now? Do I ever do this? Not too often. Do I have knowledge of it? Yes. Can I fall back to it if I'm struggling with something in an algorithm? Absolutely yes. So you're doing things here in this class that are kind of fundamental and rudimentary, but they're kind of building up your overall skill set and confidence of what you're doing. I mean, I know you say, I learned so much in calculus, all those methods for integrating and differentiating rules. How much do you use those every day? No. Do you use them occasionally? Yes. Sometimes you have to go look things up. I look things up when I need to look things up to refresh my memory, but it's still good to have them. If you were to leave, maybe like the tech school example that you were talking about during the icebreaker, you maybe never had an opportunity to learn that because that was the way that level of teaching went. And as an engineer, you're supposed to be able to know how to go discover stuff and be thorough on stuff. I certainly feel that in the consulting work that I'm doing. They pay me a lot of money, and I feel like I have to give them a very high quality amount of output. So at any rate, I've got a partial overlap case going on here right now, and so the sum limits are going to run from 0 to n. So we look at the sum limits, and what do we have inside our argument? We're multiplying, pick another color. Those two guys are in our summand, I guess, integrand for integrals, summand for sums. So those two waveforms get multiplied together, and they're right up in here. Those 3 values, or n values, if I let n move on out. So that's going to be 1, since the pulse is of height 1, and then this exponential decay. So I have k is equal to 0 to n, and I'm summing a to the k. This is a classic from calculus. The finite geometric series is the name for this. And the blue box equation is what I find in my Shams Outline Series Mathematical Handbook. Has anybody ever bought a Shams Outline book? It's something that was popular when I was in school. They still make them. You probably go to the internet and look for a table, like geometric series. I'm sure there's a wiki page on it. I won't do that at this moment, but at any rate, this is the general result for that geometric series, but because it's kind of been my characteristic to show a little proof of that, I'm going to show a little proof of that. So suppose S is this sum of values, 1, which would be r to the 0, r squared, or r squared all the way up to r to the k. So there's S, r times S would be r plus r squared plus r cubed This is a mathematical proof. You call it a back of the envelope type calculation, but this is like a rescue means to get your brain working again. What did I do there? I just did something, but that makes this proof work. So I'm following what I've done in the past. So I have S and R times S. So now what I'm going to do is I'm going to subtract.
I have a question. Did you mean to write the last expression as r raised to the k plus 1?
Yeah. My pencil is just... Yeah. A new version of this got put on my system when it got updated to Windows 11, and yeah, it's about the best I can do with the steadiness of my hand. So now I'm going to subtract, and on the left-hand side, the subtraction is going to be pretty straightforward. S minus RS. And then on this side, on the right-hand side, I'm going to notice I'm going to get a lot of cancellation going on in there, right? So what's going to survive is 1 minus r to the k plus 1. And then you can just rearrange that. Say s is equal to 1 minus r to the k plus 1 over 1 minus r. So that's the finite geometric series for, or sum of the finite geometric series for little k equaling 1, or equaling 0, I picked the wrong color, up to k, oh, I used A rather than R. How do I remember that? And I have this one committed to memory, whereas the one I put in the notes I don't have committed to memory. This is the one you probably saw in calculus. You always think of it as, it always starts at 0, and then it goes up to some value, like this case k. So when you're finally writing the sum, it's 1 minus that ratio r to the one integer greater than the upper limit, divided by 1 minus the ratio r. Does anybody remember that or vaguely remember it from calculus? Good. I'm just trying to make it slow enough to make sure you get going on this all well and fine.
I have a question, Doctor. Like the ones you've highlighted, are you going to provide like a formula sheet if that is needed in the exam?
Yeah, there is a formula sheet. It was on the old website, and I've got to go rescue it because it's somewhere. I don't even know where it went to. My old website got taken off the air finally last week, so I'm having to go SFTP into that old web server, which I have access to. I've been promised access. They're not going to take it away. All the videos, all the everything, and rescuing things off of that and then moving it. So yeah, good question. I do have a crib sheet on that. I'd pull up the old website, know exactly where it is, but on the new one, I don't know. I've been frustrated with it to some extent, and it's impacted. I wrote into Slack yesterday because of the frustration that occurred over the weekend. The guys, when they said, we're moving you to WordPress, I said, can you help me get started? So they converted a couple of websites for me, but I'll say, what did those rascals do on documents that were greater than 8 megs, which is the upper limit they set? They linked them to the old website.
Correct, and it's no longer.
Yeah. And that stuff wasn't obvious to me, right? Because I looked at the web page and I saw the link, I clicked the link and it worked. It was like, and now I'm realizing they left it dangling at any moment's notice, and I'm discovering that.
Have you thought about like adding that to your OneDrive and then putting that link through your OneDrive?
Well, does OneDrive can I do that in OneDrive? That was a
Because I think the university provides for our email address, there should be a Microsoft OneDrive subscription attached to it.
Yeah, I have Dropbox that I've used for many, many years. I know I can do it with Dropbox, but I can also put big files in Slack. So the lab class is going to have my GUI slider control, which has a Windows library associated with it. Those are like 13 megs or something. I'm going to give those to you guys today. Those are available. That's how I'm going to fix that. So and understand that over here in Slack, you can put large files in there, very large files. Some of you are going to scan your papers and you're going to have really big things, and some of you are going to be more leaner and meaner. Don't be excessive though, because it takes forever to do it. I brought this is my iPad and Apple Pencil. My printer didn't have ink in it last night, so I have solutions with me electronically, and I guess the reality is I pretty much have been able to give up paper. Is that true for most of you? I know if I was to go talk to Dr. Plett or Dr. Trimboli, because I can't get the printer to work for me up in the office anymore either, but everybody's been different, right? Every faculty member, how quickly could you give up paper? I have my pencil on my tablet, which I bought in early January of 2020. I told you that story already. I wasn't sure why I did that. I thought I'll try to switch off of paper, and then COVID came along, and then it was instantly a hit. It's been very valuable since that time, and now I use it as my engineering notebook. Okay, so for our problem at hand, we fall into the standard geometric series. So there is our second solution, and I guess I was doing that in orange. So that's our second piece. First piece was 0. Second piece is this guy here. Oops. And now we have to go the last step. The last step is where we slide further to the right. So I'm taking the case where n is greater than n minus 1. So that means that this particular value right here is now, I grabbed the wrong one. That's not what I wanted to say, because I'm looking at it wrong. This trailing edge of the pulse is greater than or equal to 0. So n minus the quantity n minus 1 is greater than or equal to 0, or strictly greater than, I guess, because this case over here has the equality on it. So it has to be greater than. So now I just finish off that sum, and that sum has got the sum limits running from n minus the quantity n minus 1 up to the leading edge of n, a to the k. So I can plug that directly into the geometric series sum formula over here and get the answer, or I can do another slick maneuver, which I am in favor of you learning and playing around with, the idea of doing re-indexing. reindexing a sum is just like changing variables in an integral. Changing variables in a sum is actually easier than changing them in the integral, because in the integral you have to come up with the differential, you have to take into account the sign, and so on. In the sum, it doesn't matter. And I guess what I'm saying, that if you're summing from like 0 up to 20, you could take your sum limits and you could go n equaling 20 up to 0, would just be reversing the order of it, and there's no differential where you'd get a sign change like you would in an integral, right? When you change the limits around in an integral, remember, you'd get a negative sign because your differential would have a negative sign in it. So here I didn't change the order of the sum. I didn't sum down rather than sum up, but I just simply changed the variable. So I have this this idea. I'm going to let k be replaced by k minus the quantity square bracket n minus parenthesis n minus 1. And what that is doing is I'm trying to make sure that my limit, sum limit, is going to wipe out to 0. So I'm going to take and replace k by k minus something that's going to make the limit start at 0. So I'm trying to make sure that limit starts at 0, and then whatever I'm subtracting in here, namely what's in the square bracket, gets added to the top. So I'm subtracting the same thing from the top limit of the sum as the bottom limit of the sum. So rather than summing like this interval, I just shifted it over to sum a different interval. It's the same width, it's just where I start. And when you do that, you have to put that change of variable inside k. So k is replaced by that same quantity. But now what happens is this piece right here pulls out in front, because that's not a function of little k. So that is sitting out in front all by itself. And then you can go back to using the standard geometric series sum formula. I'm not going to dwell on that a whole lot more, but what I'd recommend you do is look at what I did here and then see how the blue boxed equation works. The cheat sheet has this blue box equation on it, by the way, so you always have that. It's just, how do you want to do it? What I'm going to do for that cheat sheet, I'm going to try to dig that out, and I'll put it in Slack, okay? So you can grab it off of Slack, and then I'll eventually put a link into it too. But I'm pretty sure I can find it pretty readily. It's possible that it's on this computer. I'll look for that during the break if I have time. Okay, so we finished that up, and now we have a 3-part solution, or 3 cases, and they're written out here. And then if I plot that piecewise function, and I keep making that same mistake, there's what it looks like. So until the pulse arrives, until the signals arrive, the output doesn't start, and it starts charging up. And then after it fully is engaged in the exponential decay, then it starts discharging. So that's what's happening there. Let me jump over to Jupyter, since this is a really good time to talk about something that I have in Jupyter. This notebook is the notebook that's on the web page under, just so you know where it's coming from, Jupyter Tutorial Notebooks. It's this Chapter 2 notebook is what I'm looking at right there, and you can check out the PDF rendering of it from there. The other notebook I was looking at moments when we first started class is this notebook, and this one was designed to get straight to the point for the first and the last homework problems, which I'm still have yet to talk about today. But at any rate, this one is an example of programming in Python, so that's why I decided I would talk about that one here. So it's at least I think that's what it was. I may have just got myself confused. Yeah, there it is. No. maybe it is over here. I was looking at it this morning when I was eating breakfast, and then maybe I lost track of where it is. Yeah, there it is. So here, this is exactly, this pulse response is the problem we just went through, and I wrote it up in Python. So here's what we have to capture. We have to capture that three-part function in code in Python. If I wanted to just have a piecewise solution and I wanted to be able to plot it in Python, I could write a function that I could enter an argument n into through an array, and it would produce an output that is exactly that piecewise solution. That's a good programming exercise, right? I think it is. If you can do that, you can just do just about anything in the future. So let's just see how that would work in Python. So in Python, it's called a def for a definition, and a definition always begins with a colon at the end, and then you get to give it a name, and then you put arguments in. You can put in types optionally in Python, but I'll let you explore how you can put in types. Types would be whether they're integers, floats, or strings. Those are the three basic types in Python. And then there's variations on that, but here we can put in arrays. So it turns out that n is going to be an array. A is just going to be a parameter. It's going to be a float or an integer, and n is going to be an integer. And Python is sloppy in that sense. If you're writing it in C, you'd have to say exactly what the variable type with it is. I'm going to let you decide how rigorous you want to be. I'm wanting to be as least rigorous as possible. Are you good with that?
Yep.
Okay. Will you get into trouble ever for that?
Yeah.
Yes. But, I mean, quick and dirty is kind of what we're into, trying to prototype something rapidly and then tune it up later. So Python doesn't force you to put the doc string in, but with the doc string is in here, you'll see down below here that as soon as I go to use pulse response and I hit Shift Tab, you can see my doc string is in there that I wrote. If I did not put a doc string in, it would just simply list the variables that were created as arguments, and it wouldn't say anything much more than that. So at any rate, the first thing I do is I know I'm going to put in an array of integer samples, n. That's going to be an ND array, NumPy arrays. And so the first thing I want to do is dimension up an array to hold my output. So I'm going to use zeros just like you would use them in MATLAB. I'm going to create an array of zeros that matches the length of my input array. Does that make sense? That's a placeholder to store my outputs into, programming-wise. So I do that, and now I use a very standard Python technique of setting up a for loop. And the for loop is going to use a function called enumerate. And if I was to go inside of that and go Shift Tab, you would see the definition of an enumerate object. So what is cool about an enumerate object is that if you wrap enumerate around an array n, it will return as it steps for something in enumerate. Enumerate returns both the index and the value of the index at the index. And I need both of those in my calculation. So I could have just typed for k in range, and that's what I have over here, range length k, and then I could have run my loop along and I could have done things normally, but here I need both the values of n that are held at that index, and I need the index itself. So I get both of them at once when I use enumerate. Change the code if you want to in this example, and just see how it would work the other way. So now I can do an if statement, and notice always when I'm starting another command, I'm putting a colon at the end. It said for, and this is basically like in C, you would have a curly brace or something. In Python, it's the colon. So the colon is sitting there, and it's saying I'm going to have a bunch of statements inside, and Python ends this for loop with nothing. The indents go away, though. So there's an indent running down here that when that's gone, I'm out of that loop. Now, this is a hard thing about Python. You've got to use tabs, and the tabs in Jupyter are always 4 spaces, and they're exactly what Python expects. So it's quick and dirty again. Python avoids some things, but if you disobey that, you're going to get funky error messages. So be on the lookout for that. So the for loop ends, and the if and else also ends without any closing syntax, because that's the way Python works. This very last statement here, return, is not associated with any of this code. It's just returning at the level of the define, which is spaced over by 4 as well. So it said return my array y, which I dimensioned up as zeros at the beginning. So the if is if nk, the value at index k, is less than 0, I'm going to put in 0, because that's what my piecewise function has in it. And then I get to use elif, which is else if nk is less than or equal to n minus 1, then I'm going to put in the value of the second piecewise component, and ampersand is same as raising it to a power in Python. I'm just going to put everything in as the math is written out. Notice that if I wanted to be more pedantic about things, I could use logic. So I could have elif nk is greater than or equal to 0, and I can put in a logic, and just the way you would say the word and, if that's true. So then that would be another way of doing the logic. It's fine this way, though, because of the way I have it set up. And then finally, the last case is down here. So then what I would do is I would do Shift-Enter, and I've compiled it. Nothing changed in it, but if I would have changed something, like done that, there it was smart enough to say, you didn't really change it. But if I would have put 1 in there, it would have not been happy. Trying to save some work for my computer, that's cool. So now I'm going to plot it. Now I'm going to show you one last thing, and then we'll take the break, but I want you to know that a debugger is available right inside Jupyter. How many of you are fond of debuggers? Yeah, yes and no? Would you like to know that a debugger does exist?
Yeah, it's like a blog.
Yeah, exactly, but there's a little bit more to it. What you have to do is I'm going to make some space by turning off that file listing, and then I'm going to go from turn it off of simple mode, and then I'm going to say enable debugger. And now variables, a bunch of variables all over the universe. Python is object-oriented, so it has variables galore, and if you aren't careful, you won't even know what you're looking at. But what I'm going to do is I'm going to go, now I can set breakpoints. I'm going to set a breakpoint in there, and I'm going to go down to this cell, and I'm just going to run this cell. This cell calls pulse response multiple times, but it's going to stop on the very first call to pulse response. So I'm just going to do Shift-Enter in here. Now it's gone back up to debug my function that I just wrote, okay? And now, because I'm inside that function, if I look at my variables, I can see what they are. They're what I put in. Good at this point. Now I step it. Here's my step to next. If I wanted to step in to another function, if I wanted to go into zeros, I would step in, but I don't want to step into zeros. I just want to step over it. So I'm going to step over it. I've stepped over it, and now, lo and behold, it's telling me I just defined y, and I can see what's inside an ND array, and you can see there's a bunch of other variables stored inside that object, but I really don't care to look at it right now. I mean, it's all in there, but it's there. And then I can continue stepping, and right now I can see what my outputs are from enumerate. I can see what K is and what NK is. I should be able to see them, and if I can't, I just know what they are. I have to drill in to find that, I think, in this case. There's some things about this debugger that aren't as useful as if I was in VS Code. In VS Code, you can debug much the same way, except in VS Code, I would have the ability at this point to hover right over a variable and I would see what it is. But this is still not bad. I mean, you got to take what you can from what you've got. I mean, nothing can do everything, right? There's always a pro and a con to everything. So I just wanted you to be aware of that. I could then run that to completion, or I could just simply say, I'm out of it. And then if I'm out of it, I could turn off the debugger, and then I could go back to the simple, and I'll open that up again. Now I have to minimize that. So now I could go ahead and run this whole thing. And there it is. So I ran a bunch of cases through here. I ran different values of A, different lengths N, to just get different pulse responses. Sound good? That was a waste of time if it was working towards a homework solution, because you don't need to be this comprehensive, but I wanted to just use this as an opportunity to show you how to write a function in Python so you can wrap things up and make something reusable. And what I'm currently doing in my work at ARCA is I prototyped a whole bunch of functions, a whole library of functions for something I'm working on in my project there. And then once they were all developed and pretty much tested in the notebook, I moved them out to a separate module of code, which is now more manageable. And then I pushed everything to a Git repository just yesterday so another team member can see what I've been working on and have it, not all the functions in the notebook. They're convenient for you, they're convenient for all this coursework, but when you want to share stuff and have a team interaction, I sometimes prefer to just move things out into a separate function. And if I was to move things out to a separate function, then they would be an import, and this would be the name, of the module that I created that was just pure Python. I'll explain that sometime later. Let's take a break though, and we'll be back at about 9:35. That'd be 15 minutes.
Is it okay if we turn in a Jupyter notebook as our PDF or something?
No, I don't want to have to run everybody's notebook.
If it's a PDF?
If it's a PDF, but I'd like to have it parsed, and I'll talk about that. I'll give you some thoughts on that after the break. I'm going to stop the video or pause it.
Sorry.
So in the notes here, example 2.6, which follows right where we came from, I skipped over Mathematica. Mathematica was in there just to let you know that, hey, Mathematica, you probably know, is powerful. What can it do? So you can read about that if you want to. This was some Python examples that I put together for convolving two rectangles, convolving a rectangle, and an exponential decay. Check. What did we just do? We did a rectangle and an exponential decay. What do you have in the homework? You have a step and an exponential decay, right? Except one of them's running backwards. I'll talk about that problem later. That problem is a mind-bending problem unto itself, and it explains. It's trying to emphasize to you that with DSP, you can run things backwards if you want to. There's no reason why you can't in an algorithm run it backwards. If you're talking about a circuit and you're going to put an input into it, we can't make time run backwards. You just can't do it. So it's kind of just opening up the possibilities in your head to say, I could run this backwards. You're right, I could step backwards. Have you ever really thought about that? I don't think about it that often, but it is something that happens in practice. Like if you're having to smooth an image, let's say, for better, giving it better quality, what can you do with convolution in an image? You can move around with what's called the kernel or impulse response in 2 dimensions, and you can go backwards and forwards, up and down the page. There's lots of freedom available in discrete signal processing. You can run things backwards and forwards. You can find out about a function called filt, which scipy.signal has and MATLAB has. So filt is filtering twice. So you filter the signal once in the forward direction, bring it through, and then after it's been filtered, you take that array, flip it over, and filter it a second time with a time reversed. What do you think that does? An interesting concept. When a signal goes through a filter, it picks up a certain amount of group delay or phase shift applied to the signal, and this would be for audio processing, of course, too. If you spin it around, because of a property we'll look at eventually, the phase, it gets wrapped down the first time it goes through. If I flip it over and send it through a second time, the phase gets unwrapped, but the amplitude response gets applied twice. So that has some really nice properties that double the amplitude response, frequency response amplitude of a filter, and the phase distortion gets removed the second time. But what's wrong with it? You have to wait to have it processed a second time. But if you were doing this for analysis, it's probably acceptable. Like maybe a nuclear detonation occurs somewhere. I'm just giving you a military example. Somewhere on the Earth. It's picked up by seismic sensors. It's noisy. There's other things going on. We're trying to decide, what's the signature of what we just picked up? Maybe we can use some techniques like that where we don't have to have instantaneous response. We can take the time to filter part of the record captured from the seismometers or whatever a second time. Does that make sense? We can do things like that. It is mind expanding though. So here I had 3, and I go through the cases, setting up the signals, drawing the pictures and all that stuff. And then I talk through just doing the convolutions in here. And some of the notation you see floating around in here was when I originally wrote this out using an environment called IPython. And during the break before you were all back, I just went into PowerShell and I got pointing at my virtual environment. And if I type IPython here, I can start doing commands. I can import things. Like here, you can see in shadowy text, if I just hit my right arrow key, it will say, okay, I'm going to import scipy.signal. I'm kind of clunky at using this, but I could go import. I type SK and immediately remembered I was in here doing scikit dspcom.sigsys. So now that's in here, and now I can just start doing things. I would have to import you've probably seen in the notebooks, you'll see me use a % pylab in a notebook, or like right here. In IPython, that's called a magic. What does it mean to call it a magic? It's just the creator of it, but do you have, what's your interpretation of it?
I don't really know. I've just used it a lot. I've used it for like properties, assigning building.
But somebody thought the idea up, and why they called it a magic, to me, I had to learn about it, just like, okay, it does something, and so IPython, which is under the hood of what Jupyter Notebook became. IPython existed first, and then the notebook came along much later. But magics, there's a way of listing off the magics, and those were on my website too, but that document is not available right now on the new version. But what %PyLab does is it will import all of NumPy into your workspace. It will import all of Matplotlib that we use. And that's primarily what it does. And if I type inline, it will put the graphics right in this screen, which I generally don't like to do. But it's telling me right here it's deprecated. So in version 3.9, I can still run with it. If I go further out on the time axes, it's not going to work anymore. So in the notebooks that I've shown you, I've tried to get away from using PyLab up here. Instead, I'm importing all of NumPy, and I'm importing all of PyPlot from Matplotlib, and then I get the same impact. And then I'm saying to Matplotlib, I want the graphics in line. And then I'm saying down here, I want the graphics to be scalable vector graphics, so they're much sharper looking than if they were bitmap PNG files, which is what they are by default. If you're saying, wow, there's so much stuff to this, there is. You just learn a little bit at a time, and then you learn more. But magics are kind of nice. There's other types of magics out there. I don't use them very often myself, but this is the one that I use frequently. I don't want to bother to type commands, and since I'm holding myself back using an older version of Python, I know I can get away with it. Again, I'm trying to be somewhat of a cheater, so I don't have to do as much typing just to get something up and running. And Control D lets you get out of here. I'm back. Okay, so back over to where I was. I'm not really going to spend any time on this, but you can look at it and you can see what I end up doing to do convolutions in here. I thought it was right here. Why am I not seeing it? Okay, it is right here. So I'm going to go into the SIG-SYS module, and I'm going to use convolution sum. This is very good, very powerful, and I use it in the beginning of the course like this, but I soon don't use it anymore because I'd rather just use a function called lfilter, which will just take the black box idea. A signal comes in, and it goes through a difference equation representation, and it comes out. But this sum is very close to what we were just talking about. It's actually the exact same thing. We were talking about as an analysis tool, and when you use it, you get to tell it the X signal that you want to convolve with the Y signal, let's say, or H1, and then in order to get an axis for plotting the output that makes sense, you have to give it an axis of integers that matches the X array and an axis of integers that matches the H1 array, and then what comes out of this function is exactly what you want. So it's available, and it's pretty handy, and it's used here, and it's used, like this looks very familiar to what we were just doing, and you can define your signals accordingly. You can put padding on them if you want to, so that you can get some padding at the output. And I'm not going to explain a whole lot because for the homework, I know the very last problem, I want you to use L-filter, so I want to be able to explain that today. I don't want you to try to use convolve on that. But as a handy function for just doing analysis, it's beautiful because it works. If it's a real-time thing, the L-filter is going to be what we're going to use all the time. But we have to have a difference equation representation, and right now you don't know the difference because I haven't quite got that far. So I'm just skipping over that, and I'm going to land here at properties of LTI systems. Very important stuff here to go over. So if you want to cascade two systems together, and this is the whole thing behind the last problem in the homework, it's cascading, right? If you've looked at it, does everybody agree? You've got a function, a system, and another system following it. You can do a double convolution. First convolve the input with the first system and then convolve it with the second. If it happens to be linear and time invariant, which it is in order to have this convolution even mean anything, then we can take advantage of the commutative property of convolution, and we can change the order if we want to. So these three are all equivalent here if we wanted to view it together. If we have a parallel connection of systems, then we can go through the math that tells us that convolution is distributive. So we can form the output as passing through the individual systems and summing the output, or we could sum the impulse responses together with appropriate zero padding, of course, so that you could do that as a convolution if you wanted to. If it was done using L-filter, which I'll be explaining before we get done today, then you can do it that way, but you have to use another function to add the difference equations together. So I probably won't talk about that today, but I did write something in the SIGSYS library for doing that. Okay, so for working one homework problem in particular, this is the way we want to go because you're told the system is linear. I'm opening up my tablet here so I can find that problem. It's problems 2 and 3 use the things I'm talking about right now, so I just have to go back to 2 is causal, 3 is the third problem, which is 219, is stable. So use this on problem 3 exclusively. Don't try to do it from the definition of bounded input, bounded output stable. That's fine, you can prove it that way, but this problem is designed for you to take advantage of the fact that it's LTI. So if the system is not LTI, you can't use this. So be on guard. I mean, I could give you a homework problem later or an exam problem where the system is not LTI and you can't go ahead and use this property. But here you can. So just like anything, you have to know when you can and when you cannot. You just use your assumptions and drive it on through. So this is an if and only if property, but it's an extremely powerful property. What it says is a system is bounded input, bounded output stable if the absolute sum of its impulse response is bounded or less than infinity. And then you can turn this around, and that's what the if and only if means. I can run this backwards and forwards, and the proof works, and it's a property then. And I can say, if I have a stable system, I know that this sum is finite as well. You're using it the other way around there. You're verifying that it is stable by checking that the absolute sum is less than infinity. So I talk about the proof, but I'm not going to go through the proof. But I will look at an example or two here before we leave today. So does that sound good? You can use that, and I want you to use it. It makes the problems very easy, and it makes it very clear. The other property, which is not,
So basically, Dr. For an LTI, if the sum is not infinite, then it is
bounded. Yeah, it's stable. That's correct. If you want to think about why this works, it's kind of like visualizing what is the amount of gain that this system is applying to the input. And because it's doing the sum of the absolute values, it's looking at the worst case scenario is what it's doing. So that if the system had spikes in it in the impulse response, which were 2 1s plus and 2 1s that were negative, you'd say, oh, that's going to average to 0 at the output always. But if I put in a particular type of signal that would be positive and then negative, where the impulse response is negative, then I would add and I would get that greater value. So it's being pessimistic. It's saying, it's taking into account the fact that a signal might hit this at a resonant point and get a greater output rather than averaging to 0. And that's because you see the absolute value in there. Okay, a second property is this one, and this one is not written out the same way, but this is used on the second problem. A system is causal. In other words, it doesn't anticipate the arrival of the input if its impulse response is equal to 0 for n less than 0. So if the impulse response is non-zero for n less than 0, it's going to try to predict the future with the system. And I have a little page on that over on the website. It's under course materials, other course materials, this guy right here. I'm not going to go through the details, but you can look at it and see how you can look at the convolution sum and establish that the impulse response has to be 0 for n less than 0. And that's this picture here. Since I stopped over here, though, let's go back and just let you go see that this example has got several examples in it, and this is some nice examples on doing convolution sum. So it's got some more examples in here. It's got a generic example, and then it's got a couple of other examples of signals in here. And it's got this technique, which is more like what you learn in 2610 of using a table. Here's a case where geometric series is involved, which is kind of nice too. Hovering around what you have to do in homework problem number 1, where you have to set it up and then do the calculation. So in spite of the odds, I'm not leaving you in the dark, in the dust. You just got to be able to harvest the resources that are out there. And I brought this in my backpack on my bike. This, if you have bought the book, this is how heavy it is. This would be hard to catch if it was coming at you fast and not get hurt. It's pretty heavy because it's not printed on newsprint paper. It's on, quality paper. I think you get less quality paper on the cheaper version of the book, but just thinking about how that works out. Okay, so this is the second problem makes use of this. And we can look at a case in point. Okay. Other terminology that signal processing people use is they'll go beyond the impulse response and just say a signal is causal or a sequence is causal if it's 0 for n less than 0. It's a warped term, though, because causality really applies only to a system. It doesn't apply to a signal, but it's just a term that gets picked up. And then two other properties that are in here are FIR. And that's just saying that if the impulse response is of finite duration, then it's called an FIR system. So if it was a causal system and it was FIR, the impulse response samples would all occur starting at greater than n is equal to 0 and going up on the positive axis, but there'd only be a finite number of samples up there. And that's a type of filter we use a lot in applications, the FIR filter. And then the other type of impulse response is infinite, where it tapers off, and we've already seen an example of an infinite type of causal impulse response waveform, and that's where the exponential decay is in there. That's an IIR impulse response, and it's causal as long as it starts at greater than or equal to n is equal to 0. What makes FIR popular is that it's stable so long as the impulse response values have finite magnitude, because you have a finite sum of impulse response values, and as long as the magnitude of those values is finite itself, then it's also stable. So that's why people really like FIR filters. But like in audio, let's say I want to get a nice sharp cutoff frequency response for my filter, I can do it with a lot less numerical calculations with the IIR filter, but I'll have more phase distortion, but I can do a lot better job filtering with less math. The FIR filter can do no phase distortion, but it takes more taps to do that. It takes more resources to do that. So we just don't have one size fits all in the filtering world. And I'll get back to as I think about what I know about audio, I play brass instruments, remember, I don't play guitar, but if you think back in the history of music, some of the very nice special effects that are still used by guitar players to this day are not FIR filters. They're an analog filter, but they're some sort of phase distorting mechanism that goes on. I'm thinking of the wah-wah pedal as an example. You know what that sound is when you hear it? It's basically a filter moving back and forth across the spectrum, and you can tune that filter in real time then, and that gives you that effect. It's nice, right? If it's done correctly. If you're just goofing around, you can make an awful sound, but any special effect in music can be both beautiful and, not wonderful to our ears. But that's in the ears of the beholder, of course, because that's what art is, right? Nobody interprets it the same way. Okay, there's another set of nice examples in here that I'm not really going to spend time on, but this is just going through some cases of impulse step and exponential and going through the analysis for stability and causality. I'm doing this because I'm trying to make sure we have some time to talk about problems. Here's an application of using the infinite geometric series, which we have at our disposal already, right? Because we have the finite geometric series, all we have to do is take the upper limit and replace it by infinity, and then what was sitting over here on the finite geometric series, remember, was 1 something like that. It was actually capital K, but what happens if the upper limit there goes to infinity, that a to the k plus 1, what happens to that term? as k goes large. It will go to infinity if a is not magnitude less than 1. But as long as we make it stable, which is what's going on here, we get the situation that this part of the note shows us, that it will be less than infinity, it will be stable using the LTI stability theorem, and that tells us also how the geometric series, infinite geometric series, works. And they're actually intimately tied together. And if you're wondering about geometric series and digital signal processing, they are just intertwined all the way through this course. You don't have to worry about a table of integrals like you would in continuous time to look at, properties and stuff. DSP things often, distill down to a geometric series. So refreshing your mind on it is not a waste of time. We'll come at it over and over again, and we'll just use geometric series and get there quickly. Is that good? For me, it's wonderful. It's like I just get to use same ideas in a different context over and over again. Okay, we have a little bit of this in the homework, so that's why I have to get to this point. And this is opening the door to what goes on the rest of the semester. It's the LCCDE. It's a subclass of LTI systems that can be represented through an nth order constant coefficient difference equation. And if you notice, LCCDE also works for differential equations, so it's the same idea from electronic circuits. Linear constant coefficient differential equation. For us, though, it's always going to mean difference equation. And this blue box is it. This just tells us how the input and the output of the system are related. And the coefficients, the constant coefficients, are AK and BK. This is a nice, cute way of writing it, but this doesn't tell us how we calculate the output from the input. But if you look at this, you can see all I have to do is rearrange it, and I can get y of n, which is when k is equal to 0, on the left side, and put everything else on the right-hand side. Or, like I've already said, for homework problem number 1, it's running backwards. So you could arrange this so you could solve a difference equation that's cranking backwards in time, if you wanted to. So a simple example of getting an LCCDE is the accumulator. And this is a popular building block in digital signal processing, an accumulator type function. The accumulator is somewhat mysterious because the accumulator all by itself is an unstable system, but whenever it's used in practice, it can be made stable by having other things going on in the system. And I'm going to refer you back to your earlier exposure to the integrator for continuous time systems. Is an integrator stable? If you happen to put a DC value into an integrator electronic circuit, what does the integrator do? It just starts ramping, positive or negative. It hits the dynamic range of the electronic circuit itself, like the op amp, and it flattens out. In DSP, the accumulator here can do the same thing. It will try to get bigger and bigger, and it will hit a floating point limit, positive or negative, and saturate. But it doesn't make it a non-useful building block. It's actually a very powerful building block. So the accumulator is taking all the past values of the input up to the present input and adding them up to form the present output. So think about this in terms of causality. Is this causal? There's no n value beyond n that's used to form the present output. See that? Everything is past up to the present. So it's definitely causal, and that's one of the things that makes it powerful. So there's the accumulator. In this form, though, the accumulator looks like a pain in the butt, because you've got to add up everything from minus infinity up to n and just keep doing that over and over again. But then it's kind of like you shake yourself and you say, wait a minute, I've been looking at this all wrong. if we form the backwards difference between the output, two outputs of the accumulator, what we'll have the present output minus the previous output from the accumulator. And what's going to happen over here on this side is if I take the present output, which is when n is equal to n, and then I subtract over here the sum running up to n minus 1, everything's going to get annihilated, and I'm going to end up with just x of n. So just rearrange that now, and we can see, aha, the accumulator is very efficient, extremely easy to implement. All we're going to do is get the new output from the accumulator by taking its previous output and slapping on the new input. Does that seem cool? I mean, it's so wonderful, and it does form a difference equation. This is a very simple first-order difference equation. But the block diagram, mirror that again. The block diagram is wonderfully simple. It just says we have a summing node, we have a one register delay element, one sample delay, and we feed that back around into the accumulator. And that's how it works. In terms of instability, just like an integrator in analog electronics, a constant goes in at the input, and it keeps circulating around and adding up, and it's going to blow up. No doubt about that. But we can use this effectively in a cascade and in other signal processing operations. Second example is our causal moving average system. Causal, again, because we're only taking past values of the input up to the present values of the input to form the output. So this could be viewed as a difference equation right off the bat, because we're seeing that we have an output in terms of present and past values of the input. That defines a difference equation. But we can also synthesize a different form of difference equation if we just think about how this thing is working. The impulse response of the causal moving average system, if we fire a delta into it right over here, is going to look like a rectangularly shaped impulse response. We'll have u of n minus u of n minus m2 minus 1 as the impulse response. So the impulse response of our system is a rectangular pulse. And if we think about writing that as a convolution of an impulse and a unit step, we can move down here, and we can do this as a cascade. So can write that as a convolution. If we convolve anything with a delta function, we reproduce that anything. So this just tells us that a way of getting at the impulse response for the moving average system could be as the first block there to the left as a difference between two impulse delta function blocks, a time delay block, and another system that has impulse response u of n. And that would be the accumulator. We send a delta into an accumulator system, put a delta in right here, okay, that makes sense. And remember again that the impulse response definition assumes zero initial conditions. So when we start this input-output experiment out, we're going to have that one sample delay register will be set equal to 0. So we will get a delta back to a step. That was noticed over a week ago, though, too, that a delta and a step are related to each other through an accumulation operation. And a backwards difference goes from the step back to the delta. So I this out as a picture now, as a block diagram. The accumulator system is cascaded with an attenuator, and then in the middle here, this is a parallel connection of two systems, right? One is a direct wire at the top, and then the other one just delays the signal by M2 plus 1 samples. And then there's a gain block at the beginning. So we've built our causal moving average system as a cascade of systems. And you're probably thinking, oh, that looks nice and complicated. Why did we do that? Why would we do that? Well, let's see. I'm forever going to be doing this all the time, but this is the difference equation for the first stage. You just take the present input and subtract the input delayed by M2 plus 1 samples. Second stage is the accumulator. The accumulator just has to take the previous output and add to it the new input. So if we look at building this up as one system, we see we're a lot more efficient here because the first subsystem involves just the subtraction in here. So that's one operation, one subtraction, and then we have to do one multiplication. So one multiply, one subtraction. What do we have to do down here? To do the accumulator, we just have to do one addition. This is already done up here. This is the interstage point, and then this is the addition to form the accumulator output. Back over here, when we first looked at this moving average system, here we have to do M2 additions and one multiplication. So we're trying to look at the efficiency. A couple of additions, addition, subtraction, one multiplication per point. See, I'm trying to get at the idea that looking at different topologies can be more efficient from an implementation standpoint. Less real estate in an FPGA, less clock cycles in a programmable DSP microcontroller to get some output. Have to have more storage memory in one versus the other. I mean, there's other trade-offs in there, but those are all things that we like to deal with when we're coming up with a design. This is a silly example, difference equation that's nonlinear, but this is one that when I was reading a long time ago, but learning about how a calculator might calculate the square root, it does this with an algorithm that iterates to get a square root estimate. This is a difference equation that takes a constant as the input. What do? I press on again? Yeah, it's coming back on. Dr. Trimboli's going to call this in because he teaches in this class, and he said last week it did not quit in 2 hours, 3 hours time. I said it's going to quit on me this morning. I know it. And it just did. He's going to help me with it. At any rate, this is put in a constant, which is an estimate of a square root, and then you iterate on it multiple times. In other words, run the difference equation, and it estimates the square root. This is a novelty. It's not part of this class, but it's just intriguing, right? Difference equations are around us. So now we're going to look at classical solution of linear constant coefficient differential equations. This is a bigger subject. It's a much bigger subject for the second homework sheet, but it shows up in one homework problem. And no one brought this up yet, but let me just drive down to that, because I'm going to be very specific in my hinting here. This is problem 4, okay? So in problem 4, I say in the hints page, you can do this using the classical solution of difference equations, which is like solving differential equations with a homogeneous response in the particular solution. Those words mean anything in your memory bank from differential equations. We can do that. We'll talk through simple cases of that. But you can also just do a recursion. So in this problem, you're given the difference equation, right, in this homework problem. I'm robbing time from working on other homework questions, but let me just try to do a little bit of this. No, I didn't write that right. So you can recurse on this. You can say y of n is equal to so you can take that problem statement, and you can recursively get to the output. You can crank on this in Python. You can use lfilter, which I still haven't mentioned. At any rate, you can recurse on this. You see how that would be? I could just put an input in. I can put a delta into this, and then I can just start increasing. N is equal to 0. Nothing will get through to the output because the delta doesn't come in until n is equal to 1. And then you can assume 0 initial conditions for impulse response. So y at -1 is 0. You can just start cranking this, and I'll just show you where this appears in an example in the notes. So that's what you have to go back over to. I'm going to skip a lot of the math here, but I'm just going to go down to an example. Here's an example in the notes for this difference equation. So this is a difference equation in the notes. It's already written in recursive form. It's very similar to the homework problem, like super similar. If you look at it carefully, compare it back and forth, it's very, very similar. It's just another one of these practices, though. So what you can do here is you can say, rather than going the neat difference equation classical solution, you could do the recursive solution. So here it is right here. For the first order difference equation, you can solve it out and identify a geometric series out of it. You just start iterating on it. I'm iterating on it in here for this particular notes example, but in the homework it says find the impulse response as a function of the constant A, right? So just use this iteration approach. You will come along, you'll get partial answers, and then you will come down ... and say, oh, I see something coming out of this. I see a difference equation coming out of this. See what I'm saying? That second to the last line, y of n equals all these terms. You break that up into two pieces, one of which is a geometric series. In the homework problem, there's actually only one term in there, but you will get there in just, about this much space on a sheet of paper, iteratively. So go for that one that way. Okay, time is ticking rapidly right now. So just to give you some background on getting in and simulating things, there's an example here on using the Python filter function, lfilter. And this is how we go from a difference equation representation for a system into an output for an arbitrary input. So we use lfilter. And I talk about this in the notebook examples. This is just all the things that lfilter can do. But lfilter, you give it the coefficients of the difference equation. And right now, we're only talking about feed-forward difference equations, so we don't have any y coefficients. This is feed-forward and feedback coefficients. But if I was to go over to the notebook, I will go into here. This is the hints for the last problem right now. You've got a cascade of two systems. There's the impulse responses, and then you can get the coefficients, and you can use L filter to go from input to the output. And I take you partway through that in here. I just say synthesize an input that's alternating in sign, and then notice I'm using L filter, and here in the code I'm just going to put the impulse response coefficients directly in here. Just load them in manually, and then put the input in and the output comes out. Take the output out, feed it into the next filter, and the output comes out. Simple enough. Have some of you looked at this already to know that I've really laid this out, I think, pretty well in this example notebook. I've given you some of the outputs. It's just more of the same. You're going to use different input types. This input type and then this input type. So I worked part A already. You just have to work B and C. Work A, though, included in your solution.
Do you want us to work that by hand or can
You can do it entirely in Python and Jupyter.
we? Okay.
That's the plan. That was my plan.
Okay.
You can do it by hand, but you don't have to. You can do it all in Jupyter, because I want to force you to kind of get into, simulating and just seeing how things crank on through. Okay, I want to look at homework, the other homework. So let's go to the first homework problem right here. This is problem 2-3. So what you have to do is you have to set up the convolution sum on this. And I'm thinking that I did this in the other notebook a little bit nicer than this for doing the math on it, but I'm going to go to my solution and I'm just going to go write notes on it right now.
Will you post your solutions after the?
Yeah. I've got them right here, so I'm ready to roll. And Friday, you're going to ask me when on Friday. My day ends at midnight. No, my day doesn't. I'm going to say you're going to tell me my day ends at midnight. Can I turn these in at midnight in Slack? And I can see the date code. If you must, you can do it that way. I will look on Saturday morning when I'm eating breakfast. I'll say, okay, I get everybody's paper here. Now I can push out the solutions with that same password. But that's the idea. Sooner the better. I mean, I'll be taking inventory and I'll be knowing what I've got in Slack, and I'll move it out of Slack. So that'll answer that question. But let's go over to here. Just do this for a second or two. So problem number 1 is an analytical solution. So I think I wrote this out somewhere, but I don't remember where. So I'm going to take U of N or U of K. That's what we have to do, right? We have to do that, and then here's the next step. I'm going to plug in what I've got to do. U of K and H of N minus K. So when I plug in what is going on in this problem, I'm going to have A I'm going to have that. I have u of, I'm just plugging this in, face value, that, and I'm going to have that. So, what are you going to do next? I mean, this is just writing it out verbosely. It's kind of like throwing in all the junk that you can, and now you've got to pound this down.
Which problem is this again?
This is problem text 2.3, problem number 1. So here's where the action is. That's where the action is in terms of setting your limits. You want to use that product to set your limits. Does that make sense? Because one of these step functions, the u of k, turns on at some point and runs out as a 1. The other one, if you rearrange it, is just multiplying it through. It's going to be k minus n. So that one's going to turn on when you go in the opposite direction to set your limits. So depending upon what n is, it's going to have a flipping point where it's going to control the limits on your sum. That product of the two step functions determines what your limit should be. Once you look at that for different values of n, I'll tell you, I'm going to give you a very helpful piece of information. Case 1, n greater than or equal to 0. Case 2, n less than 0. So these are the two, this is the switching value here, when n is equal to 0, and I'll put the 0 point is going to be in case 1, n greater than or equal to 0. So when you go into these two step functions, that will set your limits, and then you'll be able to do a sum. And when you do the sum, they are both finite geometric series, or infinite geometric series. I mean, they're both going to run to infinity. Some of you have worked on this already. Is that making sense to you if you've looked at this in detail? There is going to be a going to infinity in both cases. So you're going to have an infinite geometric series. You're best doing it and then changing variables in the geometric series. But there's different techniques of doing that. I want you to just, grind your way through this. You'll get it. And then you'll be able to make it match what the simulation is, which we have in the notebook.
Could you show how you set your limits, like what the limits will be with those two situations?
Oh, and they come out right from here is what they do. So, well, here's what you can do. Here's what I would do if I was doing it again. I'm running out of time, so I don't know what I wanted to do something else, but I don't know what that was going to be. You want to plot right? So you want to plot this one, and this one is going to be, so when k gets to be, k is equal to n is where this thing flips. So this step function is running, no, it's running forwards. I think, yeah, it runs forward. So both of these run forward. So when k is equal to n, then this step function turns on. When k is less than n, then it's off. Agreed? Then the other one here is just u of k, so the other one is turning on over here. So what's going to go on here between these two step functions is when n is less than 0, your limit is going to be the product set by the product of these two. So you have two different limits that are going on in this thing right here. In other words, this is going to go out. The pen is not wanting to draw right now. That's going to go out, and now you're going to be looking at what these limits do. Okay? And it's going to have to do with what is n. Is n greater than 0? And this is, that's 0 right there. I've given you a lot. You'll see this on the video too. It'll fall out in your hands and you'll just see what the limits are. The upper limit, it will be infinity under all circumstances because that's what's going on here, right? This is always going, never stops. So the upper limit will be infinity. The lower limit is what's going to change depending upon what n is. And then you'll be able to sum the series. So I want the series summed also. I don't want it just a summation sign. I want it equals to something because it's an infinite geometric series. Okay. I am pretty much out of time. What were the other questions on? I was going to show you an example of a proof. That was, what was that problem? What?
2.23.
2.23. Okay. I was just going to pick something out of that. I was going to show you real-time DSP in the Jupyter Notebook, but I will do that for the lab students up in the lab because that's something that you need today. You're going to make some recordings for 20 seconds so that you can have a test vector to play with. Okay, 223. Which one do you want to pick? You've got B and D.
B.
Okay, okay. So you have to do stability, causality, linearity, and time invariant. You have to have an argument written down in words and maybe using math. So I don't have time to do all of them. Which would you like to see? Which one is, since you posed the question, which one would you like to see? I'll do one of them.
Linearity.
Okay. So for linearity, what you're trying to show is you're trying to say that you want to be able to show that that is going to be equal to y1. By the way, this is y. Then. So that's what you have to show. And then you can just individually go into that. You can use the fact that this is the relationship and plug that in. And it doesn't matter whether the argument is n or n squared. It will still superimpose as expected. In other words, I can do it t operating on the whole thing as x of n squared, or I can do it individually to get the individual responses, and that's what you just have to work through. You have to fill in the dots on that. I think one of the harder ones, though, is one of the other ones, like, is it causal, for example? That means that the output depends on the feature. Well, the thing that you have to argue with the math, and what you want to do is if something is not true, you just pick one instance, like say, see, this case, it doesn't work, it's invalid. So if it's not causal, you just say, pick n is equal to -5, let's say. what's going to happen there, you're going to get -5 is going to become 25, right? So the present output is going to use that future input. You know, the present output would be n is equal to -5, it's going to go ahead and try to grab x at +25. You see what I'm saying? The logic is pretty simple like that.
Yeah,
Be clear and concise, though. Maybe scribble it out on a piece of paper and then clean it up so that what I see is not just, you know, you're scribbling here and there. That aggravates me to no end. It's like, where is the answer? It's all over the map. So scribble it out quickly for your own liking. And I do this all the time. I'm working on the computer. I still pull out a pad of paper and still have to scribble things down. And then eventually I organize it on the computer. If anybody wants to ask me more, I'm going to go up to the lab right now, so you can follow me up there.
If we use those intuition to answer, like say for example, I use n as 2, so I see that I need to look at x at